talk a few minutes about springs, not the season, but the bouncy things like that are on your garage door and in your bed mattress. Um, I'm not going to get. I'm going to take a slightly different approach to springs. I'm not going to get into discussing or talking about Hooke's law because that's the force the spring applies to the object it's attached to. I'm not going to get into the derivation of the work that the spring does. That can be re-derived on your own by looking at that work is the integral of the force. And you can kind of see from, if you integrated force with respect to x, it comes out to be the work equation, and that's not the correct work equation because I forgot a 1/2. And I'm not going to talk about the potential energy of the spring, which is just the negative of the work equation, if I can write correctly. I'm not going to talk about any of these things. What I want to talk about is I want to go through some examples of when a spring is attached to some mass, frictionless surface, and I want to talk about the properties and parameters that are often looked at in these types of problems as the box is having simple harmonic motion, meaning the spring is going back and forth. And that's really kind of what I wanted to take a look at. So I'm going to begin with a box attached to a spring, and they're always going to be attached to the spring. And I'm going to begin with a box that's been pulled beyond the spring's equilibrium point. The equilibrium point, that's our defined position that our displacement x is equal to 0. That's the natural length of the spring when it's horizontal. There's a slight change to things when the spring is vertical, but it's not a whole lot different. And I want to just kind of look at each of these positions. And so we pull this box out, and we're just going to hold it there for a second before we let it go. And basically, when the box is in this position, we are at our maximum amplitude because we are at our maximum positive displacement. Which means, because we're at our maximum displacement, my spring force is at a max. But what you have to remember is, in Hooke's law, the spring force has a negative sign in it, which means it's opposite in direction to the displacement. So I'm at my maximum magnitude for the spring force, but the spring force is really going to the left, or it's in the negative direction. That's important to keep in mind, because what this means is we have a negative acceleration. Because my spring force is at a max, my acceleration is also at the max. Now, whether I'm holding the box out there, holding it at rest, or it's actually moving back and forth, when it's moving back out here and it's at its maximum amplitude, for just an instant it is at rest, which means velocity is equal to 0, which means kinetic energy is equal to 0. Because we're at maximum displacement, our potential energy is at a maximum. And really what this means, my total energy is my spring potential energy, or my elastic potential energy. These are the things that are happening when the box is clear at its positive maximum displacement. What I want to take a look now is, when I let this box go, or as it's moving to the left, what is happening. Let me just take a second and redraw this example. So now the box is moving to the left. We're not at maximum amplitude. We're not at our equilibrium point. So what does this mean? This means we're still on the positive displacement, but it's not a maximum. This means my force, my spring force, is still negative, and it's decreasing. It's going down. Because my x displacement is going down, my spring force is also going down. If my spring force is negative, I have negative acceleration, and if my spring force is going down, my acceleration is going down. Because I'm going to the left, I do have a negative velocity. And since my acceleration is negative and my velocity is negative, that means my velocity is increasing as it moves to the left. If I have increasing velocity, I have increasing potential energy. Now, I do have a non-zero displacement, which means I do have potential energy, but it's decreasing because my displacement is decreasing. And so my total energy at these points consists of kinetic plus my elastic potential energy. My next position is when the box is at the equilibrium. So now my box is at equilibrium. That means x is equal to 0. If x is equal to 0, my spring force is equal to 0. If my position is equal to 0, my potential energy is equal to 0. If my spring force is equal to 0, my acceleration is equal to 0. And what I'm experiencing at this point is maximum velocity to the right, or a negative maximum velocity, which means my kinetic energy is a max. If potential is 0, kinetic energy is a max, my total energy is all kinetic energy. So these are my criteria. This is what's going to be happening when the box is at the equilibrium point. It's important to understand the box doesn't stay there. The box is going to pass through the equilibrium point. The spring wants to pull the box to the equilibrium point, to its normal stretch length. But as it's pulling the box does have energy, and the box then proceeds past the equilibrium point and starts compressing the box. So the spring just doesn't pull the box to the equilibrium point, it pulls the box to the equilibrium point, and the box goes beyond the equilibrium point, compressing the spring. So let's take a look at what happens at that point. So now we have a box beyond my equilibrium point, moving to the left. I now have negative displacement, and it's increasing. It's getting bigger. It's getting more to the left. If my displacement is increasing, my spring force is increasing. However, if my displacement is negative, the spring force is positive. The spring is now pushing the box in the positive direction. That's why the spring force is positive. If my displacement is increasing, my potential energy is also increasing. With a positive force, I have a positive acceleration, which is also increasing. However, the box is still moving to the left, which means I have a negative velocity. Positive acceleration, negative velocity, opposite directions, means my velocity is going to be decreasing, which means my kinetic energy is going to be decreasing, which means my total energy is back to being kinetic and potential. Not quite done. Let's take it to my full compression point on the spring. So this is my full compression point on the spring, which means I'm at my negative maximum amplitude, which means I'm at my negative x maximum displacement, which means my spring force is at a maximum. And because my x is in the negative displacement, negative direction, my spring force is still positive. It's still the spring is still pushing the box to the right. With my positive spring force, that's a maximum, I have positive acceleration, that's a maximum. Because before my velocity was slowing down, it came to a point where it's zero. My kinetic energy is zero. My total energy is completely potential energy, once again, at this point. Except for the signs of like the displacement and the direction of the spring force and the acceleration, the magnitudes of all these terms are the same as when it was at the positive maximum amplitude. And then the box is going to be pushed back. And as it's pushed back, we can go through the same analysis. As it's being pushed back, it's actually going to be similar to this situation. As it's going to the right, it's actually going to be similar to that situation where it's initially going to the left, except the signs for displacement, spring force, acceleration, and velocity are all going to be different. They're all going to be switched. We cross our equilibrium point. These conditions are the same. We go beyond the equilibrium point. These conditions are the same, except for the signs being opposite. We get back to the end of positive displacement, and I'm back to my first frame, and we repeat. So these spring problems are kind of an interesting problem because what they require us to sometimes think in these terms of what's going on with acceleration, velocity, kinetic energy, potential energy. It's really, they're very straightforward. You just have to take your time and think carefully about what is going on with the box. What's the direction of the spring force? That tells us the direction of the acceleration. The direction of the box and the direction of the acceleration tells us whether it's speeding up, slowing down, what have you. Problems get a little bit more complicated when we're not on a frictionless surface, but when we're encountering friction. But the same principles with force and acceleration and velocity still apply. So I hope this was a little benefit for you. There you have it. There you go. Good luck.